Yeah. Good morning, everyone. Can you please take your seats so that we can start? Before we get into the scientific contents of this 31st page meeting, it's my pleasure actually to welcome Dr. Juan Borrego, who is the representative of the mayor of the city of La Coruña, who is hosting this event. And I'd like to give the word to him before we get into further details. I already mentioned to him that page has beat a new record. We have had more than 900 registrations, and we have participation of 32 countries, again making a record for the event. I reminded him that we are for the fourth time in Spain. It always started many years ago in Salamanca. We had Pamplona welcoming us, Alicante, and now A Coruña. Please, Dr. Juan Borrego.
Muchas gracias. Good morning, everyone, and welcome to A Coruña. It's a great pleasure for me to welcome you to our city. In other words, welcome to your home. Because A Coruña is the city where no one is foreign. Please feel the city like your home. Health, technology, thought, community and progress have been the mainstays of this city for many years. A Coruña has always been a benchmark in modernity in Galicia and Spain, and always will, with an international perspective and with such good fellows as Congress like this. Thank you. A Coruña es una ciudad atlántica, una ciudad acogedora por naturaleza, una ciudad dinámica e innovadora, una ciudad cosmopolita que marca tendencia, una ciudad diferente, una ciudad de vanguardia, una ciudad referente en el campo de la sanidad, en el campo de las nuevas tecnologías, en inteligencia artificial o en el ámbito de las TIC. Somos testigos de los últimos avances en el ámbito sanitario, científico o tecnológico, gracias sobre todo a congresos como los que tenemos la suerte de acoger en nuestra ciudad y del que este es un gran ejemplo. Y es muy importante para nosotros, y hablo en representación de nuestra alcaldesa, poder celebrar aquí este 31º Congreso Internacional de Farmacología Clínica, un foro 100% internacional con ponentes procedentes de distintos países. Es un honor contar con los mejores profesionales en este campo, reunidos aquí en Palesco. Estamos seguros de que de este encuentro saldrán nuevas ideas y se definirán las nuevas líneas de actuación en el campo de los datos, de la farmacología, de la medicina. En definitiva, avances importantísimos en uno de los campos que precisamente hacen más feliz al ser humano, que es la salud. Y, por supuesto, invitarles también a disfrutar en la medida que puedan de nuestra ciudad, porque se viene por primera vez a La Coruña, pero nunca por última vez. I would like to thank you everyone for attending this Congress. Thank you for visiting A Coruña, and please enjoy the Congress and the city. You are welcome in the first time to visit to A Coruña, but this is not the last time. Thank you very much.
So I take the opportunity also to thank the City Hall and the Mayor of La Coruña also for their support for the meeting, which has contributed a lot to the organization. Thank you very much. Without further ado, I think we will be having a few sessions later today and tomorrow with further announcements, but it would be interesting to highlight that we will be asking for candidates to participate in the scientific organizing committee, and we are going to make further details later on tomorrow when we have a slot for announcements. I would like now to ask Thomas Dorlo to introduce the scientific program, which we will kick off now, and enjoy your day and the whole program up to Friday.
Thank you, Oscar. So my name is Thomas Dorlo. I'm the chair of the Scientific Organizing Committee. Oscar already thanked a few people, but I would like to thank you, all the participants, for submitting a record number of abstracts as well. We had 422 submitted abstracts, so almost half of you have submitted a scientific abstract, which is an amazing feature, of course. And, well, Page would not be Page if we didn't have the Page community to rely on, so we would like to thank you for that. We had 109 oral abstracts, a few hundred poster abstracts, and a few software demonstrations. And also, more than usual, we had 23% methodology abstracts this year, which is quite remarkable for any conference, but we really like to make an effort to spend some time on methodology at Page, so we really would like to thank you also for submitting these methodology abstracts. Out of the 109 oral abstracts, we have selected 21 abstracts that fill the oral program, I will be highlighting some of the conference sessions soon. All of the abstracts were reviewed by the Scientific Organizing Committee, which consists, besides me, of 16 other people. It's a good representation of both academia and consultancy and pharma. I would like to announce the opportunity that we will have a call to join the Scientific Organizing Committee next autumn or end of summer. You will find more details through the usual communication channels. Probably if you have registered for Page, you will receive an email about this. But we would really like to try to push you to apply for membership of the SOC. Again, as Page, we are reliant on the Page community, and we really want a good representation of the Page community within our Scientific Organizing Committee as well. So some of the highlights this year. Today we will have a session on pediatric extrapolation, both a regulatory perspective and some case examples of what is pediatric extrapolation, and mainly some examples where it went well, where the pediatric extrapolation was successful. We will have a tutorial on machine learning and pharmacometrics and several methodology sessions. Also representing the high number of methodology abstracts that you submitted to us. Tomorrow there will be what many think is the highlight of Page, the Louis Scheiner student session with 4 excellent PhD presentations, and we will have a keynote on circulating tumor DNA as a pharmacodynamic biomarker, and as well the Stuart Beal methodology session that we do every year. And on Friday, if you survive the social evening on Thursday evening, we will have a session on QSP disease models and a session covering some new model diagnostic procedures. So, without further ado, I would like to start the scientific program with the first session, which is on new modeling approaches. So, please have a fantastic Page, and I hope that you will enjoy the program. Thank you.
Okay, so good morning everyone. My name is Marie-Laure Chenel and I'm a principal consultant and team leader at Fermetis.
Good morning, my name is Rob ter Heijnen, hospital pharmacist. I'm not sure which name is here, but it's not me. I work at the Radboud University Medical Center, Radboud Applied Pharmacometrics.
So we are delighted to co-chair this first session about new modeling approaches. So we have 1 hour, 3 talks, 15 minutes each, and followed by 5 minutes of question and answer. So please, when asking question, introduce yourself by giving your name and your affiliation, even if you are a star in pharmacometrics. So our first speaker, Nikolaos Alimpertis, unfortunately could not make it. He was sick over the last days. I think he's feeling better today, but he was not able to travel. So he has kindly make a recorded talk. So we will listen him, and then his PhD supervisor, Panos Manteras, will come on stage. So just a brief introduction. So Nikolaos is a data engineer by background with an MSA in computational biology and bioinformatics, and is currently doing his PhD under the supervision of Panos Manteras. And his research area is in pharmacometrics and data science, and he has also interest in mathematical modeling, focusing on the dynamic of infectious disease. And the title of his talk is somewhat provocative. The estimate for the absorption rates constant in pharmacokinetics and pharmacometrics are wrong. A new era based on the finite absorption time concept rises. So yes, if you can play the...
Hello everybody. Unfortunately, I couldn't be there. I wish you have a great conference in La Coruña, and thank you very much for your introduction. Let's start with my presentation. This work summarizes several published and unpublished papers in the field of oral drug absorption. This will be briefly presented during my talk. This is the outline of my talk. Initially, I will talk about the false assumption that break pharmacokinetics of oral drug absorption. Then I will focus on the development of FAT concept and the relevant scientific and regulatory applications. And finally, I will also briefly describe the current unpublished work. Let's talk about this false assumption. And all started from Bateman, a great mathematician in 1910 who analyzed Rutherford isotopes data. And in particular, he analyzed the time course of 3 isotopes in chain, mother, daughter, and granddaughter. He described the abundances of the 3 isotopes as a function of time. Specifically, he described the abundance of daughter isotopes with equation 1, which is a well-known bi-exponential equation, which increases initially, reaches steady state, and then declines. The key point here is that lambda d and lambda m are first-order rate constants, which are related to the notion of half-life applied initially in physics and then used in pharmacokinetics. Several years later, in 1953, Dost wrote the first pharmacokinetic book, where he adopted Bateman's equation. He applied the same concepts. The absorption rate constant, as well as the elimination rate constant, are first order. This means that absorption and elimination operate from 0 to infinity concurrently. And here this slide shows Bateman's vis-a-vis Dost equations. The two relationships, as we can see, are identical, where instead of lambda d and lambda m, we have now k elimination and k absorption. Okay, for elimination processes, the exponential character is very well known. However, the infinite time of drug absorption is not physiologically sound, since drugs are not absorbed beyond the absorptive sites in the GI tract. Drug absorption can take place even 30 minutes or 1 to 10 hours, but not in infinite time. The validity of the assumption of infinite time of drug absorption was questioned in 2019. Here it's a very simple example. The blue solid line indicates the Bateman equation. The dashed line, which is almost identical, is the simulation using our finite absorption time model for oral drug absorption. If the absorption terminates at 3 and 10 hours respectively, then the AUC is important for the fraction absorbed up to the finite time of 3 and 10 hours respectively. And this is the take-home message for this part. If absorption terminates at time tau, then the AUC from 0 to tau is the ideal metric for the extent of drug absorption. We are moving now to the second part, and this is the article dealing with the development of finite absorption time concept. and this simple model of drug absorption in the GI tract relies on the FAT concept. Drug absorption takes place in the small intestine mainly, as we can see with a thick arrow. The absorption of class 1 drugs, meaning high soluble and high permeable, terminates in the small intestine in less than 5 hours, while the rest classes, class 2, 3, and 4 drugs, may be also absorbed in the colon, as we can see with the dust arrow, but certainly not beyond 30 hours. And the high blood flow rate in vena cava maintains in conditions for the passive drug absorption. And this is a schematic of the GI drug absorption indicating the physiological time limits of 5 and 30 hours. This slide shows the first fitting results with a new model, using the models with one single input phase. As we can see here, the blue segment indicates the absorption phase, while the orange segment indicates the elimination phase. We consider now the scientific applications which are based on the development on physiologically based finite time pharmacokinetic models, PBFT-PK models, and this is the basic article for the development of PBFT-PK models. And now we have a formal representation of PBFT-PK models with 3 successive input rates for 1 and 2 compartment model drugs. These analytic model equations were used to generate concentration time profiles, assigning various values to the model parameters. Here we have some fittings using the PBFT-PK models of many of them included in the previous article. In all cases, the PBFT-PK fittings were superior to the fitting based on the classical first-order absorption models. Estimate the duration of drug absorption stages, and the drug input rates are quoted. And the triangle denotes the end of drug absorption period. These fittings, for these 4 drugs, used a different PBFT-PK model. In the first case, in paracetamol, we used the N1 compartment model with 1 input phase, while in the second and the third example, in almotriptan and ibuprofen, we used 1 compartment model with 2 input phases. And the last example of niraparib is fitted by a 2 compartment model with 2 input stages. This is the take-home message of this part of my talk. The PBFT-PK models are ideal to describe oral drug absorption kinetics. This is the first application of PBPK and PBFT-PK models to the same set of data. Here, we analyzed 6 MEX drugs, and this slide shows the fit of PBFT-PK models to the concentration time data of these drugs. Okay, the take-home message of this part is that the application to the same dataset of PBPK and PBFT-PK models enhances the understanding of drug absorption phenomena because the PBPK models are bottom-up and PBFT-PK models are top-down. Especially the previous paper exhibit correlations between simulated biopharmaceutical characteristics, meaning solubility in GI lumen, and in vivo pharmacokinetic observations. This work is the first application of PBFT-PK models to data previously analyzed with stochastic approaches. It can be seen that PBFT-PK models describe nicely the successive input rates of mavacluran data. Again, we reported the best feature of our methods in comparison with the classical models, and we reported the parameters, determination of the absorption, and the relative rates, etc. I'm quoting here the take-home message of this part, and PBFT-PK models should be used in order to reanalyze complex absorption kinetics as structural models in pharmacometrics involving absorption steps. This is the fourth section of the talk. And here, as all of us know, AUC is a metric for the extent of the absorption, while Cmax and Tmax indicate the rate of absorption. I would like to repeat that in order to calculate AUC, we need to integrate from 0 to infinity. But from our side, the AUC from 0 to infinity is an exposure metric, not a metric relevant to the fraction of absorbed drug. In this work, the bioavailability of digoxin is re-examined after half-century. In 1973, Louis Seiner and his colleagues examined the bioavailability of digoxin under fast and fed conditions. The results based on AUC and Cmax shows that the bioavailability of digoxin under fasted conditions is much better. But when they measured the urine excreted digoxin for 5 days, as we can see in the third bar plot, they realized that bioavailability was the same in both cases. And we got the same bioavailability for both formulations when we compare the relevant AUCs, since absorption has completed at 1 and 3 hours in fasted and fed condition state, respectively. The second digoxin example is from a bioequivalence study analyzed by FDA. Here, we have blood sampling for up to 142 hours. We estimated the end of digoxin absorption using RP-50PK models at 1 and 1.5 hours, respectively, for the two cases. We calculate the AUCs until the end of digoxin absorption, and we found the same result with FDA using blood sampling up to 142 hours. And the take-home message for bioavailability studies that AUCs is better to calculate it up to the determination of drug absorption, as shown previously in digoxin data. All above are in full agreement with our approach for the reassessment of bioequivalence of axitinib data that we present last year at the PAGE meeting in Ljubljana. These are the axitinib data. We have two test datasets and one reference. And the following methodology was formulated, this trapezoidal rule of the cumulative areas. If you want, you can check it on the last year abstract. And the take-home message is shown here that the AUC from 0 to tau for the assessment of bioequivalence is in full agreement with physiologically sound FAT concept. I'm closing my talk with a quick look at recent unpublished work. This is the last submitted publication. We modified, in terms of finite absorption time, the Wagner-Nelson-Lurie-Gelman plots and the deconvolution techniques for the construction of percent absorbed vs time plots. And we proved mathematically that for a single or more input phases using either one or two compartment model disposition, the ratio of the amount absorbed up to time t over the amount absorbed up to time tau is increasing linearly up to time tau when absorption terminates. And this means that we have a paradigm shift in oral drug absorption. To conclude, the FAT concept should be integrated to various applications in relevant fields. I want to say many thanks to my two supervisors, Professor Macheras and Professor Tsekouras, for giving me the opportunity to work with them on FAT modeling. We have published many articles so far based on FAT concept, and the following two books include all the relevant work on FAT concept. And this is a group that we create in order for people that are interested in our ideas. If you want, you can join. And thank you very much for your attention. Thank you very much, and I wish you have a great time there. Thank you.
Okay, so of course we would like to thank him, even if he's not listening to us. And so we have 5 minutes for question and answer. So Panos, would you like to come on stage to take the question of the audience, please? Thank you, Panos. So do we have question for Panos? Oh, yes.
Leonid Dibiansky, One Farm. I'm here. I have a question concerning it's interesting concept that you define bioavailability as ratio of AUC up to time of the end of absorption, but how to define that time if you just have data? Infinity is kind of obvious thing, but this time that you have to select somehow. Could you elaborate how we do it?
Yeah.
You would do it?
Actually, we developed two methodologies for estimating tau. The first one is a nonlinear regression analysis. We use our models, PB, FTPK models, and we feed the data. within the model of the data. We did this work extensively, and we realized that in all cases, the PB-FTPK models are much better than the classical models with first-order absorption, whether or not you use one compartment, two compartment models. So we are confident that absorption terminates at a specific time point. The second methodology relies on the last work, which has not been published so far. It relies to the classical, say, percent absorbed versus time plots. We reanalyzed many data from the literature, and we found that the initial, say, absorption stage is linear. So we developed a computerized method, whether or not we have one single input, or two inputs, or three inputs, and we determine the plateau level. So we have a kind of combinations of the data points, and we estimate tau, the end of the absorption process, whether or not we have one single or two input stages or three input stages. And actually, we very recently realized that we are able to estimate tau using either the nonlinear regression analysis or the simplest approach based on the percent absorbed versus time plots.
Okay, thank you. Do we have So if we don't, I've got one panels. So I can understand that for a drug with complex absorption, first order absorption constant is not appropriate, but I thought that for highly soluble, highly permeable drugs, so the one from the BS class 1, as they have a passive absorption phenomenon, like following the concentration gradient, first order absorption constant was, making sense. So my question is, have you compared the absorption duration estimate that you obtained from your approach, the finite time modeling approach, to the one that you obtain by deriving, like for instance, 5 half-life from the first order absorption constant?
You refer to biowaivers, highly permeable, highly soluble drugs, basically? Okay. So if you have a highly soluble, highly permeable drug, as we call it, class 1 drugs, we realize that the first order absorption process is a good approximation of the reality. But we are able now to demonstrate that for these particular drugs, the BCS1, biowaivers, highly permeable, highly soluble, Tmax is the end of the absorption process, the end of the absorption process. And on top of that is the completion of the absorption. That means we are able to estimate that more than 90% of the drug has been absorbed. So it's a new pharmacokinetic approach for those drugs which are considered as biowaivers. We do know that biowaivers can be described easily with the first absorption rate constant. This is a nice approximation of the reality. But if you consider BCS, for example, and take into account the, say, time considerations, you realize that these drugs are absorbed in a matter of 30 minutes. You certainly know that today's regulation associated with biowaivers has the finite time dissolution time in the guidelines, since, according to the regulation, very rapidly drugs are those which are dissolved in less than 15 minutes, while rapidly drugs are considered those which are dissolved in less than 30 minutes. So the concept of finite time is already in the regulation, although it is not defined as so. I realized that very recently. Intuitively, we do have, say, finite absorption time, but at the same time, we do have finite dissolution time. So all of the functions we use modeling dissolution phenomena like the Weibull function or the noise-Whitney function are all of them exponential, but they very easily transformed, modified to say, a version which involves finite time. So this is my advice for all those associated working on the biowaivers area.
Okay, thank you. So I think we have to move on now.
Can I have a question?
No, we're sorry. Perhaps in the break. So the next speaker is Robin Chaud. He's a public health university hospital assistant working in the clinical research department of the University Hospital of Saint-Étienne. And he's also pursuing a PhD at the University of Lyon. And he's going to talk about a meta-analysis of parameter estimates of nonlinear mixed effects models using approximate Bayesian computation.
So, hello everyone, and thank you for inviting me to speak at this Congress. I feel very glad and honored to be here. So I'm going to present to you this work, which is about really a single idea. It is managing to perform a meta-analysis of populational pharmacokinetics studies for a drug. In other words, we would like to do a meta-analysis of a parameter estimate from multiple nonlinear mixed effects models. But for a given drug, there might be already 10 or 20 or more published articles with all kinds of different pharmacokinetics models. They might differ in terms of structural models, covariates included, residual models, error models, etc., etc. And this might be an issue if we want to aggregate all those models into one meta-model for our meta-analysis. For example, for just the vancomycin drug, there are more than 14 models published, all with different structure. We see on the left all the 14 studies, and we see the evaluations of the parameters, the main parameters, the random effect structures, and the different type of residual error model, constant, proportional, etc. In green, those are the parameters estimated for a study. In white, the parameters that were not estimated for a study. And we can see just visually that there's almost not two studies that have the same model. There is a vast mix of model structure. The same for parameter estimates. The main one here is we have a huge heterogeneity between models. So, how could we build a single meta-model, a meta-analysis, which would summarize all the information in the literature by still considering the respective structure of each model? How can we do that? Now, a possible solution, the first one that may come to mind, is performing a meta-analysis on individual patient data, just consisting of combining all individual data for a specific drug and performing a pharmacokinetics analysis on this. This would be the ideal approach, but more often than not, we will have huge issues with data availability. We cannot find the data, the individual data, and it might be near impossible to do this. We also can do a meta-analysis, classical meta-analysis with aggregated result, aggregated estimates. This would mean pulling the mean estimates of parameters across studies, but this would not account for the structural heterogeneity and may bias the results. So, what would be the checklist for an ideal method able to perform a meta-analysis? We will need to use aggregated estimates published in the literature. We will need to take into account model structure heterogeneity, and we will need to use a likelihood-free estimation method, because calculating a likelihood function over the space of models structure is very, very hard, might be very hard. To do that, we used the method approximate Bayesian computation, which is not a new method. It might allow the inference of parameters from complex statistical models, such as the one we want to do, where the true likelihood function is unknown or unavailable. In short, because we will see more of that in detail, it relies on the simulation of virtual data and the quantification of the distance between the results of the simulation and the observation or published results. The general principle being that the better a parameterization reproduces the observed data, the closer it is to the true parameter value. But how does this work for our specific case? We're going to gather, as in any systematic meta-analysis, all the studies for a specific drug. Here again, vancomycin, for example. Now we'll need to the first step is to choose a reference model based on the literature. This reference model is the model the user, the researcher, think is the best for this specific molecule. For example, this reference model with the estimated parameters in red would be a two-compartmental study with random effects on all parameters, combined error model, and 3 covariates. So you have to understand that this reference model is already, in this work, is already our meta model for our meta-analysis. As far as this work goes, there's not yet implemented model selection. That might be a bit counterintuitive, but this is our meta model. But we'll see that a bit more later if you want. And so the goal for this meta model, this meta-analysis, will be to estimate the parameters of this meta model as accurately as possible. And how can we do that? I'm going to first define a distribution of priors for each parameters for our reference model, for our meta model. We have here 4 examples of non-informative uniform prior distribution with kind of a wide range for the illustration. And then we are going to start our simulation process. So the first thing is we're going to sample a set of parameters from our prior distribution for each parameters. We're going to sample a set of parameters. We're going to use the sample set of parameters with our reference model, our meta model M, on each study that we have for our meta-analysis. And with those priors and the reference model, we're going to estimate, we're going to simulate individual patient data for each study. Using those individual data, we're going to use each study-specific model on each data, and we're going to estimate the parameters for each model, for each simulation. We're going to repeat this process many times, 500,000 times, 1 million, 2 million times, until we have huge databases of our sampled prior, our sampled parameters for the reference model, and our estimated results on the right. So you have to understand that we will sometimes we are randomly drawing priors, and we might have completely wrong or a bit wrong parameters, leading to wrong individual patient data, leading to completely or a bit off the track simulation, and we will have to select the simulation that worked best. For that, we're going to use our estimated results, and we're going to calculate a distance between each simulated results and the result published in the literature. We will have a distance, the sum of a distance for each simulation, and we're going to select the simulation that worked best by selecting the simulation with the distance under a certain threshold, and we're going to discard the others. So what happens exactly? We remove the simulation with a really high distance, and we finally get the approximation of the posterior distribution of the parameters of each parameters of our meta model. So this is a bit, the ABC rejection is a bit of a raw technique. And we need to add another final step of post-processing of the data using the regression method, random forest, to improve estimation accuracy. It's its own method on its own, and I will not have time to enter into details in this presentation. So we have our ABC rejection technique and ABC rejection plus post-processing that we're going to try to evaluate. Before applying it on real-life data, we're going to see if the method works on dummy data that we created ourselves, on virtual data. And we are going to evaluate the performances of the method against the true parameters of values on the dummy data, estimations from individual patient meta-analysis, and estimations from univariate aggregated data meta-analysis. So what happens? simulated 11 dummy population pharmacokinetics analysis with various design, 2 compartmental, 1 compartmental, etc. And we selected a reference model to be 2 compartmental, random effects on all parameters, a combined error model, and 3 covariates. You don't have to select every parameter that were estimated, of course, each time. So this is our meta model. We do now the process of simulation. We do 2 million simulation, and we have the results of our ABC rejection technique. If we do not select the simulation, if we take them all, our posterior distribution will look like exactly our prior distribution. This is normal. And then we're going to select more and more, lower and lower and lower the threshold of distance, and select more and more studies. And we see for these 4 example parameters, central volume of distribution, the constant error, the intercompartmental clearance, and a covariate. For some parameters, it works very well. We have a nice posterior distribution for the central volume of distribution, for the constant error. But for some other parameters, which are a bit harder to estimate, which are more sensitive to variation, it did not work well. What happens next if we had, for the same parameters, the post-processing step? We see with the black dashed line the true parameter value, it's our target, in red the posterior distribution, and in green our prior distribution. We see that for the 2 parameters which worked well, it's even more precise and more interesting. For the 2 parameters which did not work well with ABC rejection alone, the results are almost unbiased and still very precise. What happens now if we compare those results to other methods? We have the forest plots of the result of our 11 studies for the 4 main parameters. Still the black dashed line, the true parameter value. And what happens with other methods? With individual patient data meta-analysis, we are very close to the true parameter value. We are almost unbiased and very precise. That is what we expect from this method. With aggregated data meta-analysis, we're a bit less accurate, a bit further away sometimes from the true parameter value. With ABC rejection alone, we are really not that good. But with ABC plus the post-processing method, the random forest, we have results which are very similar, although not as accurate than individual patient data meta-analysis. Just 2 more telling examples for the between subject variance and the clearance. We see that with aggregated data meta-analysis, in yellow, this time we are biased, but with our method, ABC plus random forest, we're almost as good as individual patient data meta-analysis. No method is perfect, of course, and for some parameters, it did not work. For this covariate, for example, even with our method, we are biased. So, in conclusion, this method might be very promising. It might really allow to meta-analyze pharmacokinetics model while still taking into account model's structure. The estimations were more precise and less biased than with classic aggregation methods. And in most cases, the performances were similar to individual patient data meta-analysis, although not as accurate, and sometimes didn't work for every parameters, of course. Speaking of, that's a limit. Speaking of limits, this method requires a long calculation time. We need to do 1 million, 2 million simulation, and it might take 1 week on a working PC, on a work PC. If my boss was here, he would argue that it might take 2 weeks for me because I always forget a comma somewhere in the code and have to do it all over again. And we have the issue of the choice of the reference model. So we've seen here that it's user-defined based on the literature. But we can argue that we think that it is the best model, but we might be wrong. And there exists some ABC extension using random forest 2 for model selection. We can compare different models and find the one that best fits the data. But so far in this work, we did not apply it yet. And finally, it's impossible to include certain studies due to data reporting data we cannot use in the reported studies, and some models are too complex for being used in this meta-analysis. Thank you for your attention.
Any questions from the audience? Please state your name and affiliation.
Nick Holford, University of Auckland, New Zealand. Well, thank you for this great introduction to my poster, which is poster number 57, which has the answer to vancomycin and gentamicin, amikacin, but vancomycin was the example you used. It has 9,000 patients, 22,000 observations with a single model. So it could be considered the gold reference standard for your simulation model that actually doesn't have a reference.
Yeah. Oh.
So if you'd like to come see me at the poster.
Yeah. Thank you very much.
Okay.
That's very nice. Thank you.
So that's the first point. The second point is, I'm guessing the population you used was what I call a geriatric population. That is to say, it was not the pediatric population. Is that correct? The studies were largely done in adults?
No, the populations were really mixed up, depending on the drug you're used to die.
No, the vancomycin one.
The vancomycin. This was just for the sake of the example. We didn't do it yet on vancomycin.
Okay, all right. Well,
but as far as I remember, no, there was quite a good mix of a population, not necessarily geriatric population.
Okay, well, you used that simply because you had age on clearance. And I just also would like to point out that age on clearance is always wrong.
Yeah.
Because age is just a ticking of a clock. Tick, tock, tick, tock. That's age. Time cannot cause anything. That's a fundamental physical principle. So using age as a covariance is purely empirical, and therefore will always be wrong. It may be a good approximation, like using a first order rate of constant, as Panos tried to convince us, but it's always wrong.
Okay.
So
Your
models based on age will always be wrong.
Yeah. But that was just for the sake of illustration. But
Okay,
thank you very much.
Yeah, please note that this is an example. So another question.
Yes.
From
out here in the middle.
Okay. Also in the back.
Jeff
okay, in the
Sachs.
back. Yeah, please.
Yeah, Jeff Sachs from MSD, and it seems that an essential step in your process is the random forest refinement step. Could you provide more detail about exactly what you're doing in that step?
Yeah, sure. It's the random forest. We're using it on the ABC data that we simulated. And it permits to modelize the link between the sampled parameters for the reference model and our estimated results. And it allows to predict the sampled priors as if we were simulating real data, real observations.
Thank you.
Thanks. A final question, if you can make it a short one.
I'll choose one, thanks. Building human predictions. So within the initial model selection of the ideal or reference model, it seems like within the model selection of the reference model, it seems like, as you mentioned, there could be bias in choosing the one reference versus another. Have you considered doing permeations or a jackknife of all of the different models to try and overcome that limitation?
No, we haven't yet, but let's talk about it later. That's interesting. What we were thinking is just using ABC extension after that allows for comparing multiple models, but yeah, that might be a very interesting take on that.
Thank you.
Thank you. Thanks to you. Thank you very much.
Okay, so our third and last speaker is Mohamed Jewouli. He is a pharmacist by background from the University of Alexandria in Egypt. He has done his master's degree in Rennes in France, and is now doing a PhD with Professor Mats Carlson and also Gustav Wellhagen. And Mohamed is interested by a method applied for the estimation of treatment effect in randomized clinical trial, and also in application to rare disease. So the title of his talk is a semi-parametric method for the estimation of end of treatment effect. So Mohamed, the floor is yours.
Yep. Thank you, Melo, for the introduction. So I'm going to present my project titled The Semi-Parametric Method for the Estimation of End-of-Treatment Effect. This work is supervised by Gustav Velagen and Mats Karlsson, Uppsala University. Yer Sultan is my master's student. So I'd like to start by talking about treatment effects in randomized clinical trials. So a treatment effect is defined as a statistically significant change in clinical outcome that is attributable to treatment compared to reference. So treatment effects are typically assessed at the end of the treatment, whether that be in absolute value or as change from baseline. And there are several methods that can be used to assess the significance of the treatment effect. Two of those are mixed models for repeated measures, or MMRM, and also nonlinear mixed effect models. So aside from their capacity to detect the significance of the treatment effect, both of those methods can also estimate the magnitude of the effect. So another benefit from using MMRM and nonlinear mixed effect models for the estimation, it is the fact that they are actually primarily structured to describe longitudinal progression data. So MMRM model the mean and the standard deviation of observations at each categorical time, and they are considered as the gold standard to handle dropouts because they make use of different error correlation structures. In contrast, nonlinear mixed effect models, they have the advantage of using continuous flexible progression equations, and they can use less parameters compared to MMRM. Which brings us to end of treatment effect and how its magnitude is estimated using the previously mentioned methods. So MMRM estimate the mean difference in a study outcome between the study arms at the last time point. Their estimate is mostly unbiased but not very precise. Nonlinear mixed effect models, on the other hand, they can, although this is not their usual parameterization, but they can be made to estimate the same difference at the last time point. However, they are subject to misspecification bias, and they can inflate type 1 error because of the sequential model building that is involved, but they can have more precise estimates compared to MMRM. So this means that we can have two methods to generate two different estimates of the treatment effect. So naturally, the question arises, what is the magnitude of the true effect? So in the plot to the right, you see an illustration of bias versus precision, which is one of the scenarios that can arise when using MMRM and nonlinear mixed effect models for the estimation of end-of-treatment effect. So the objectives of my work is to investigate the combination of both MMRM and nonlinear mixed effect models for the estimation of end-of-treatment effect. We want to know what impact would that have on the estimation accuracy. So in the main methodology, which shows to diverge from the classic model averaging methods, namely those that are based on objective function or likelihood, because they tend to use the entirety of the data across all time points to try to calculate the objective function and then do the model averaging. While in our case, we're more focused at the end of the treatment. So this is why we chose to base our work on a paper published by two statisticians, Yuan and Yin. So in the paper, they try to obtain an accurate semi-parametric estimate of a dose response curve by model averaging across two methods, an unbiased non-parametric and a more precise parametric. So they start by assuming that the non-parametric estimate was on average unbiased. Then they bootstrap to measure the error relative to the initial non-parametric estimate that they considered as mostly unbiased. Finally, they managed to develop a semi-parametric estimator that they call pi that uses mean squared error, or MSE, to estimate the best model weights. So in their work, pi was the weight of the parametric method, and 1 minus pi was the weight of the non-parametric method. So what we have done is that we have adopted their estimator and applied it to our purposes. So the models that we used to demonstrate the properties of this new method are the following. MMRM with unconstrained residual error correlation, meaning that the error variance-covariance structure has the maximum degrees of freedom. A nonlinear mixed effect model that is close to the published model and has a suitable progression equation. A misspecified nonlinear mixed effect model with the misspecification lies in fixing the slope to 0, meaning that we assume no disease progression, which is essentially not true given the data that we have. Nonlinear mixed effect model with individual model averaging, or IMA. So this model assumes two subdistributions, treatment and placebo, and then for each individual, the probability of belonging to both submixtures is estimated. So also here we have an IMA with a suitable progression equation and an IMA with slope misspecification. So our goal is to average across all pairs of MMRM and nonlinear mixed effect models. So this is illustrated in a plot to the right. So MMRM is a common factor in all averages. So the data that we used are the following: Parkinson's disease, MDS, UPDRS, placebo data with 6 time points. Alzheimer's disease, ADAS-Cog, natural progression also with 6 time points. And diabetic neuropathy, Likert pain, placebo data with 7 time points, all without dropouts. So I'm going to go through the workflow step by step. So we start by permutating to randomly allocate individuals to either treatment or placebo, assuming a 1-to-1 parallel design with equal allocation probability. Then we fit the models to the resulting data sets. Afterwards, we bootstrap 600 times, so meaning that we resample from the permutated data set 600 times with replacement, and then we refit the models. So this step is essential to calculate the error, and therefore the semi-parametric estimator pi. Finally, we repeat the process from treatment allocation to bootstrapping 100 times. So I'm going to talk a little bit more about this new method. So we named it the semi-parametric approach, or SPA for short. And pi is the weight of the nonlinear mixed effect model, and 1 minus pi is the weight of MMRM. So as previously mentioned, the calculation of pi mainly depends on mean squared error. So as the MSE of MMRM increases in relation to the sum of MSEs of both models, so does pi, and also the weight of the nonlinear mixed effect model. So MSE is calculated relative to the initial MMRM effect estimate, so initial meaning before bootstrapping, as you can see here. And while the driver of the final value of pi is MSE, there's also a covariance bias in the equation that is mainly there to account for the error correlation between the models. So once we're done with bootstrapping, we can calculate covariance bias and MSE, and therefore pi. And finally, we can do the point estimate averaging. So finally, in the methods, I want to talk about type 1 error. So type 1 error is assessed for each model. So it's assessed across 100 studies. And for each model, it is the frequency of which models detect a treatment effect that is significantly different from 0, because as according to the design, the true effect is expected to be 0. So now you see some of the main results. So this is the Parkinson's disease data set, and those are the treatment effect distributions across 100 studies. And so all model predictions are expected to be centered around 0 here, the true effect. And here, when I mention bias, I'm referring to the mean of the distribution minus the true effect, which is 0. Precision is the standard deviation of the same distribution, and accuracy is the mean squared error. So this is a case where the nonlinear mixed effect model was unbiased and more precise compared to MMRM. So SPA had also unbiased estimates, but lost a degree of precision compared to MMRM, but was more accurate compared to MMRM. In contrast, this is a case where the nonlinear mixed effect model was clearly misspecified. So SPA largely collapsed to MMRM by giving most weight to MMRM. Here's the case where with the individual model averaging, or IMA, and it had accurate estimates, even in the case when it was misspecified. And so by consequence, SPA also had more accurate estimates compared to MMRM. This is the Alzheimer's disease data set, and there's a trend here for all nonlinear mixed effect models to be accurate. So therefore, SPA, from using all of the models, also had more accurate estimates compared to MMRM. This is the diabetic neuropathy data set, and also here we can see a big contrast in the case where the nonlinear mixed effect model was clearly unbiased and also biased. So SPA lost a degree of precision in the first case, but corrected for bias in the second relative to the nonlinear mixed effect models. So also here IMA had accurate estimates, and therefore SPA that used the same models had more accurate estimates compared to MMRM. So those are the numbers that correspond to the plots that you have seen. So this is the mean squared error. And in the blue, highlighted in blue is the mean squared error of SPA. And we can see that SPA, MSE for SPA is never bigger than MSE of MMRM, highlighted in red, even in the case where the underlying model, nonlinear mixed effect model used for SPA was misspecified, as highlighted in the third row here. Finally, I want to talk about type 1 error. So MMRM had controlled type 1 error in all scenarios as expected. However, in Parkinson's disease and in diabetic neuropathy datasets, we clearly had an inflated type 1 error for the misspecified nonlinear mixed effect model. And this translated to also a degree of inflation in the corresponding SPA. Otherwise, SPA had controlled type 1 error in the other scenarios. So to look more into the cause of the type 1 error inflation, so this is an example of MODIFIT, and this is the Parkinson's disease data set. This is the good nonlinear mixed effect model. So according to the visual predictive check, we can see that the model fits the data well enough. Then we introduce the slope misspecification, and we can see that it mainly results in a loss in precision and an overestimation as highlighted in the upper interval here. So we believe that this misspecification was enough to cause the type 1 error inflation that we have seen, which also affected the corresponding SPA. So finally, those are our conclusions. SPA had better treatment effect estimation accuracy compared to MMRM. SPA resulted in a more controlled type 1 error compared to the nonlinear mixed effect models. So IMA was unbiased in all scenarios and had better treatment effect accuracy compared to MMRM. So SPA is a compromise between MMRM and nonlinear mixed effect model and is sensitive to the properties of those components. Finally, SPA is a tool that lies on a continuum of methods that can be used to estimate treatment effects. So the choice to use SPA can be subject to scenarios and objectives, but also the expectation of bias and precision in the models that are intended to be used. Finally, I would like to thank the Pharmacometrics group and PKPD group in Uppsala University for the discussion and the feedback, Apotheca Societatum for the travel grant, and UPMAX for the computational resources. Thank you, and I'm ready to receive questions.
Okay, thank you very much, Mohamed, for your nice presentation. So, yes, we have time for a couple of questions. So, can you introduce yourself, please?
Yes, I'm Laura Zweb from Leiden University. Yeah. I think it's a very nice method to get this weighting between the two models. So I do wonder if one of the models, like the IMA, is very good, then why doesn't your pi, your hyperparameter, go fully towards that model? Is there a way to do that, maybe?
Well, in the settings that we investigated, IMA was unbiased, and this is because mainly that we're investigating settings where there is no treatment effect, but we don't have evidence that IMA is proof to misspecification in all other scenarios, while MMRM is well documented to being proof to misspecific or being unbiased in general. So this is why we think that MMRM is a better, but we can certainly modify the reference method, but we think MMRM is the most suitable in this case.
So, I mean, if you have two models and one of them is performing better, then maybe the semi-model can converge to that side instead of somewhere in the middle?
This is what I'm trying to explain. So, in our cases, it was good, but we hope that it's good in other cases. So IMA is relatively new, and we're investigating its robustness. But if we expect that it might not perform as well as MMRM in other scenarios, then it means that it's better to base our analysis taking MMRM as a reference.
Very clear. Thank you.
No problem.
Thank you. No question? Well, yes, we have one at the back.
Jeff Sachs from MSD, again. Thank you for the nice talk. In one of the examples that you showed, there was a clear difference in the mean estimates. And if it is true that MMRM is unbiased in most examples we'd be interested in, is it possible to use the difference between the means to identify when there is a model misspecification? There was at least one example where there was this dramatic difference when the nonlinear mixed effects model was misspecified. So can this be used in any way as a test to identify that?
I think in a way this is what is being done using this method. So we try to estimate the best weights. So when we calculate the mean squared error is calculated in relation to the initial MMRM estimate. So this means that if the mean difference is not big or is close to zero, then we are going to have more weight on the nonlinear mixed effect model side, especially if it's more precise or it has less, so a smaller effect distribution. So this is technically what is being done in the background using this semi-parametric estimator.
I guess I was thinking in terms of actually determining that the model, the nonlinear mixed effects model, is in fact misspecified, so that one could then change the model and get an even more accurate and precise estimate by perhaps combining the models.
I think, yeah, I understand, but I think it's more of what you're describing, I guess, is more of integrated in the process more than an exclusion criteria. So it's integrated in adding weights. So this means it's also kind of an exclusion criteria, because also if the mean is very far away, then the nonlinear mixed effect model is not going to gain any weight, as in this example. And this is why SPA collapses to MMRM. So I understand, but I think what you're describing is also integrated in a way, but it can also be an exclusion criteria a priori before even using the methods. Yes, I understand.
Thank you.
Okay, that concludes it for the first session of PAGE. I would like to thank all presenters and you, of course, the audience. And right now there's a coffee break and poster session 1, and we would like to welcome you back at 11:30. I heard good news about a vancomycin poster, but there are also other posters as well, so please make sure you look around. See you back at 11:30.